You know, when you think about the light from your phone or the Wi-Fi signal connecting you to the internet or even the radio in your car, have you ever stopped to think what that stuff actually is? Well, it turns out they're all the same thing. Today, we are diving into the incredible story of how electricity and magnetism, two forces that seem totally separate, are actually just two sides of the same coin. And get this, figuring that out solved one of the biggest mysteries in all of science: what light really is. So let's start with a question. What on earth could possibly connect a gigantic, chaotic bolt of lightning with the calm, controlled light coming from your phone screen? I mean, they couldn't seem more different, right? But trust me, by the end of this, you'll see they are basically the same phenomenon, just playing by the exact same set of universal rules. All right, so to understand this, we've got to go back to the very, very beginning, to the simplest possible thing in this entire story. A single electric charge, just sitting there, not moving. It might not look like much, but believe it or not, this one tiny, still point is where the entire Symphony of Light actually begins. Now, this stationary charge isn't just taking up space, it's actively changing the space around it. It creates this invisible web of influence that radiates out in all directions. We call this the electric field. You can't see it, you can't touch it, but if you drop another charge into that field, oh, it will feel it. It'll feel a definite push or a pull. Here's a really cool way to picture it. The electric field is like an invisible instruction manual written into the fabric of space itself. Every single point has a little arrow telling any other charge that comes along, hey, you, go this way with this much force. It's a static, unchanging map of force. But what happens when the thing creating that map starts to move? Okay, this is where things get really interesting. The moment we take our little charge and get it moving, create a current, the universe reveals something that was hidden before. A whole new force just appears out of nowhere, a mysterious force that, as it turns out, people had been using to navigate for centuries. And this slide just lays it out so clearly. On the left, you've got your static charge, doing its thing, creating only an electric field. But look at the right. The second that charge starts moving, something new pops into existence around it, a magnetic field. All of a sudden, that weird force that makes compasses point north isn't some separate mystery anymore. It's tied directly to electricity. And motion. Motion is the key that unlocks it. And check out what happens when we get that motion organized. This thing here is called a solenoid. It's basically just a coil of wire. And when we send a current, a stream of moving charges, through it, we get this beautiful, structured, and totally predictable magnetic field. It's undeniable proof. If you organize moving charges, you get an organized magnetic field. But that got scientists thinking, if electricity can make magnetism, could it work the other way around? For the longest time, everyone thought this was a one-way street. Electricity could make magnetism, end of story. But there was this brilliant scientist, Michael Faraday, who just had a hunch there was more to it. He felt deep down that these forces were connected on a much deeper level, and that the link just had to go both ways. And wow, his intuition was about to change everything. And here it is. His incredible discovery known as Faraday's law of induction. What he found was that if you change a magnetic field, like, say, by waving a magnet around near a wire, that changing field actually creates an electric field out of thin air, which then pushes the charges in the wire and creates a current. So you see, it's not just a connection, it's a creative dance. A moving charge makes a B field, and a changing B field makes an E field. They can literally create each other. This is where our story hits its crescendo. Enter the Scottish physicist James Clerk Maxwell. He looked at all these different pieces of the puzzle, the rules for electric field, the rules for magnetism, Faraday's new discovery, and he did something absolutely monumental. He wove them all together into one single, beautiful, and unbelievably powerful theory. And these are his famous equations, the 4 rules for this whole electromagnetic symphony. Let's just quickly break them down. The first one's easy. Electric charges make electric fields. Got it? The second one says you can never find a north pole without a south pole. They always come in pairs. The third is Faraday's big discovery. A changing magnetic field creates an electric field. And the fourth, which has Maxwell's own genius touch, says that a current or a changing electric field creates a magnetic field. Together, these 4 laws explained everything known about electricity and magnetism.
But buried deep in the math, they held an absolutely mind-blowing secret.
See, Maxwell wasn't content to just write down the laws. He started to play with them. He asked a brilliant question. What happens if you're out in empty space, with no charges or wires anywhere, and you just create a little disturbance, a little ripple, in one of these fields?
The math was crystal clear. If you make a changing electric field, it will create a changing magnetic field. But that new magnetic field is also changing, so it creates a new electric field, which in turn creates a new magnetic field, and on and on and on. It's a chain reaction. The disturbance doesn't just fade away. It travels through space as a self-sustaining wave, electricity and magnetism leapfrogging off each other forever. But the craziest part was the speed the math said this wave had to travel at. So, Maxwell plugged in two numbers that were already known from basic lab experiments, constants that measure the strength of electricity and magnetism. He ran the calculation, and the equations spit out one very specific, non-negotiable speed for his wave, 299,792,458 meters per second.
Now, you have to put yourself in his shoes. He just derived this number purely from the laws of electricity and magnetism. And when he looked at it, he realized, wait a minute, I've seen that speed before. Physicists at the time knew that number very, very well. They'd measured it, but in a totally different area of science. As Maxwell himself put it, the conclusion was basically unavoidable. The speed that his equations predicted for these electromagnetic waves was identical to the measured speed of light. And that was it. That was the moment. The lightning bolt and the light from your phone were one and the same. Light, the very thing our eyes use to see the universe, is nothing more than a ripple in the electromagnetic field. A traveling wave of pure electricity and magnetism, dancing through space, born from the very laws Maxwell had just put on paper. So why is this such a huge deal? Well, first, it's one of the greatest unifications in the history of science. It showed us that the universe is simpler and more elegant than we ever imagined. But more than that, by understanding that light is just a wave we can create, we learned how to build our modern world. Every single time you listen to the radio, use your Wi-Fi, or send a text message, you are using technology built directly on Maxwell's discovery. It's just a stunning example of how pure curiosity can completely change the world. And that just leaves you with this incredible, lingering thought. By uniting just two of nature's forces, we accidentally discovered the true identity of light. Right now, physicists are working to unify the rest of the forces, so you have to wonder, what other profound secrets about reality are just sitting there, hiding in the laws of the universe, waiting for us to find the next connection?